Welcome back. This is Mr. Greenstein's Geometry, and we're doing Chapter 7.5, Properties of Trapezoids and Kites. So far, we've been talking about parallelograms, and now we're going to talk about a couple more quadrilaterals that are not parallelograms. The first one is the trapezoid, and a trapezoid is not a parallelogram because it only has one pair of parallel sides. If the other pair of sides were parallel, then it would not be a trapezoid. So exactly one pair of parallel sides. The two parallel sides are called the bases. And the bases have what are called base angles. So the base angles are always paired with each other. The base angles at the bottom here, these two, that would be considered one pair of base angles. And then these top two would be considered another pair of base angles. So they're always considered together. They're not, you don't have base angles going like this way. They're not, those are two different bases. So they're always associated with the same base. And then we also have legs. So legs are also the sides that are not parallel. If the legs are congruent, which they can be the same length, then we have what's called an isosceles trapezoid. So then we have the two bases that are parallel, and then we have the legs are congruent, then we have an isosceles trapezoid. Now let's take a look at QRST. Is this a trapezoid? First of all, let's graph it out. So I'm going to put Q, which is 0, -1, which is right around here. So that's Q. And we have R, 0, 2, which is right around here. And then we have S, which is 2, 3, which is right around here. And then finally T, 4, 1, which is right around there. So that's T. And then we'll just connect these up. We want to show that this is a trapezoid. Well, looking at it, right away we can see that RS and QT might be parallel to each other. And the way that we can tell is that we can use the slopes of RS and QT. So that's one way that we could test if this is a trapezoid. If we want to figure out whether or not this is an isosceles trapezoid, then we would figure out what the length of this side RQ is and ST, and if they're congruent. If they're congruent, and then these sides are parallel, then we have an isosceles trapezoid. So you can check that out. It's actually pretty simple here. With RS, we're going to go up 1, so that's the rise, and over 2. So up 1 over 2, that's going to be 1/2. Whereas here we have Q, we're going to be going up 1, 2. We're going to go across 1, 2, 3, 4. So up 2 over 4 is 2 over 4, or 1/2. So we can show that RS is parallel to QT. I'll leave it up to you to come up with the distances between these two sides. Now let's talk about some theorems. The isosceles trapezoid base angles theorem, the first one. And this one says, if a trapezoid is isosceles, then each pair of base angles is congruent. So first of all, we have to show that we have an isosceles trapezoid. That means that we have parallel sides and we have congruent legs. So once we have that, then we know that the base angles are congruent. So B and C are congruent, D and A are congruent with each other. The converse of that is if one pair of congruent base, or one pair of base angles are congruent, so we're going to just say A and D, and it's a trapezoid, then it's an isosceles trapezoid. So first of all, we have to say that this whole thing has to be a trapezoid, which means that we have parallel sides. And if we can just show that one pair of base angles are congruent, then we have an isosceles trapezoid, and that makes AB congruent to CD. The third is if a trapezoid is isosceles, if and only if its diagonals are congruent. So that's saying that if we have a trapezoid, which means that we have parallel sides, and it's isosceles, then the diagonals are going to be congruent. Or if we have a trapezoid and the diagonals happen to be congruent, then it must be isosceles. So both of those, it's a biconditional because of the if and only if. The midsegment of a trapezoid is special. Just like we have the midsegment of a triangle, the midsegment of a trapezoid is formed by the midpoints of the two non-parallel sides. So it splits each one of these sides into congruent segments. And there's something special about a midsegment. The midsegment theorem says this: a midsegment is parallel to each base. So that's very powerful. Just like the midsegment of a triangle is parallel to one of the sides, here it's parallel to each one of the bases. And the length of the midsegment itself is 1/2 times the sum of the two bases. So base 1 and base 2. Let's calculate the length of the midsegment of this trapezoid. Well, first of all, we need to graph it. So 0, 6 is right around here. Then 8, 10 which is right around here. So this is S and this is T. U is going to be 12, 2. So unfortunately it goes off the grid here, but it's going to be kind of around here. And that's going to be U. And then V is 2, 2. So if I connect these together, I get something like this. And you can see right away that ST is not parallel to UV, but SV might be parallel to TU. So this is probably where we're going to have the bases. And then we calculate the midsegment, and the midsegment is going to be, I'm just going to sketch it here, kind of approximately like that. Lousy drawing, but that's some kind of approximation. We're going to need to find the midpoint of S and T, and we're going to need the midpoint of V and U. And once we have those midpoints, then we can determine the length of the midsegment. Another way that we could calculate the length of the midsegment of the trapezoid is just use the formula. And the formula says that the midsegment, which is, we'll say is D, is equal to 1/2 the distance from S to V plus the distance from T to U. And I'll leave it to you to come up with the, the, uh, the distance using the distance formula. The next quadrilateral that is not a parallelogram is called a kite. And this one is special because it has congruent sides and they're consecutive, kind of like the rhombus has consecutive congruent sides, but not all the sides are congruent. So I have congruent sides here and here, and I have congruent sides here and here, but these are not congruent across here. And that makes for what we call a kite. So there's the kite diagonals theorem. If a quadrilateral is a kite, then its diagonals are perpendicular, very much like a rhombus's. There's also the kite opposite angles theorem. When you have a kite, then one pair of angles, opposite angles, are congruent. And in this case, it's A and C. B and D are not congruent. So be careful. When you have a kite, you only have one pair of congruent angles. So here's a problem working on a kite. And it gives us some angles in here. So we know that PQR is going to be 78 degrees. That's this whole angle is going to be 78 degrees. And then we have TRS. So TRS, which is just a small part of this angle here, is going to be 59 degrees. The thing that we know is that the angles in the center, like here, are all going to be 90 degrees. So we have 4 right angles. Another thing that we could probably figure out is that the angle Q over here is bisected by this QS. So if this whole thing is 78 degrees, then half of it is going to be in this top triangle here, and half in this bottom triangle down here. You can work out the rest of the numbers yourself. In the second problem, you're to find the angle F. And this is an isosceles triangle, trapezoid, and with an isosceles trapezoid, we know a lot because we know that the base angles are going to be congruent down here and the base angles are going to be congruent up here. Plus, this whole thing is a quadrilateral, therefore it equals 360 degrees for all of the internal angles. You should be able to figure out F at this point. And then finally, with this one, we have a isosceles trapezoid. We know that Jn is 10.6, so that's this part right here. This part right here. And Ln is 14.8. Then you should be able to figure out what Km is, because we know something about diagonals of isosceles trapezoids. And I'll let you figure that out on your own. We'll be visiting problems like this in our next class, and I'll see you then.